afternoon, everybody. This is Dr. Subrat Kar, Assistant Professor at School of Biosciences, Apeejay University. I welcome you all to today's webinar on uncovering the mode of action of drugs utilizing chemical genetics, to be delivered by our international guest speaker, Dr. Mohammad Al-Fatah.
Yeah.
So I will give a brief introduction of Dr. Al-Fatah to our audience, which comprises largely of students, interested students, both current and future students, as well as different faculty members from different departments of the university, as well as different organizations of Apeejay. So to give a brief introduction of Dr. Mohammad Al-Fatah, he has completed his master's from Jamia Hamdard University and has completed his doctoral studies in biosciences, biological sciences from the international reputed laboratory CSIR MTech in Chandigarh. He is currently working as a senior scientist at the prestigious A-Star Bioinformatics Institute in Singapore. He has an extensive research experience in chemical genetics, drug discovery, toxicology, and metabolic engineering. Dr. Al-Fatah has successfully established a chemogenomics profiling research platform, which is probably the only platform in Asia for high throughput screening and unraveling the mode of action of extensive bioactive compounds, small molecules, peptides, toxic chemicals, and metabolites in different areas of drug discovery, genotoxicology, and metabolic engineering. Dr. Al-Fatah has published his findings in several high-impact international scientific journals, and his extensive research has led to the discovery of the role of sulforolipid biosurfactants as an antifungal and anti-biofilm agent. So without wasting more time, I would like to invite our international speaker, Dr. Mohammad Al-Fatah, to talk to us about this very interesting topic, which we all want to hear about now. So over to you.
Yeah, thank you, Dr. Subra, for his nice introduction. And I would like to thank the Dean of School of Biological Sciences at Apeejay University for this wonderful opportunity to share my work with the faculty members and the student. And of course, there's a big thanks to Dr. Jishan. Without him, it's not possible. He's quite responsible person and is quite dynamic. And we are actually did master together. And I never seen such type of person in my life, which is quite intellectually sound and personally also very good. And I know he's quite good in science. He's quite specialized in cancer as well. So thank you all, Jishan and Dr. Atul, Dr. Subra, and all the faculty members and students for here. And before I just move, I just would like to share my slide. So I hope that everyone can see my slides. Dr. Subra, can you see my slides?
Yes, we can see, definitely see.
So this is my topic, just as Dr. Subra has already introduced about what I'm going to talk. So as we all know that the biological cell is a fundamental unit of life, and there are lots of metabolic reaction is occurring within a second, more than 1,000, 2,000. And if any function of the cell is interrupted, then that will compromise the human health. So if our health is good, then our cells should be good and healthy, and all the cellular function is controlled by the protein, and which is encoded by the gene, which is formed by DNA and RNA and follow the central dogma to produce the protein. And so any problem in a cellular function can lead to the a variety of diseases, including the cancer. Very well known that if any unchecked cell division occur in the human body and human being, then that causes the cancer. And so cells should be very healthy, and all the cellular system of the cell, like glycolysis, mitochondria, and the lots of protein synthesis, should be in a good condition and control way. And everything is controlled by the protein, which is encoded by the gene. And as we all interacted with different environmental factors, so we all are interacted with different environmental factors and that compromise the cell function. So environmental factors could be the artificial or natural, and their interaction with the cellular system could be beneficial and toxic. So how these environmental factors interacting with the cells and affect the human health is quite an important portion in the medical field, because uh, how these environmental factors, for example, the toxic chemicals interact with cell, what is their mode of action, and how this, like the, for example, the nutrients, like nutrients is good and as well as bad for us. So if we over nutrients, then that cause the obesity, but we need the nutrients to get the energy. So there are two different types of interaction of the environmental factor. For example, drugs. Drugs is quite beneficial in a health, but sometimes some drug actually is quite toxic for health. The loss of drug is good, but that also causes toxicity. That's why there are severe side effects of the drug. So how these environmental factors interacting with the cells and causing the cellular function changes is quite important question. And what is the mode of action of this toxic chemical to the cell is also very curiosity. So to understand the mode of action of this compound interacting with the cells is to be know, and why we need to know, understand the mode of action. I just would like to quote one very good example. So as you can see here, this is the famous bark of the famous tree. This is a willow tree, and this is historically this tree, this bark or whatever the component like leaf, this extract, their extract actually using for a long time in Egypt. So Egyptian use to get rid of the fever and for pain as well as some other headache problem. So, but that time, like around, this story is 2000 years back, but how, what is the component inside this bark or willow tree, they don't know until very recently in 19th century, from 2000 back, but in 19th century, chemists come to know that the component in this willow tree is actually acetylsalicylic acid. And after that, and this acetylsalicylic acid, we all know the brand of medicine is called aspirin. So this aspirin drug is quite famous before 1950 because this actually only single drug used for treatment of the pain and fever. Until 1950, once ibuprofen and paracetamol, which is quite active drug, used and replaced this drug because that is more active. But before 1950, doctor is always think that aspirin is okay, good for the fever, but this have also some dark side effect. Doctor come to know that some people have a bleeding effect, some people have some another problem due to this aspirin, but that all the cause is underestimated because they don't have any other option. So very recently, 1980, because the technology developed, all the medical instrument, new instrument developed. So scientists come to know the mode of action of aspirin and how this aspirin actually worked. They come to know that aspirin inhibit the two enzyme protein like cyclooxygenase COX-1, COX-2. This COX-1, COX-2 synthesize prostaglandin hormones from the arachidonic acid. And this prostaglandin have a two function in a cell, including some other function as well. So prostaglandin actually is cause for the inflammation, and this inflammation actually leads to the nervous system, and they just give the fever. And so aspirin, using aspirin can get rid of the fever problem. But simultaneously, if you add the aspirin, then this will inhibit the platelet aggregation formation because it will not allow to form the prostaglandin. So if less platelets aggregation, then that causes the bleeding. So that's the why people were getting the two side effects. The positive side effect was darker part of the aspirin was platelet aggregation, that's the cause of bleeding. That's why a doctor always prescribe before they giving the aspirin that whether you have any infection like dengue or you have a low platelets, then they never allow to give the aspirin drug for that patient. But since this mode of action discovery, bring back this aspirin is very demanding condition, because this is the only drug can be used to give the heart attack patient, because most of the heart attack is associated with the blood clot. So this mode of action reveal the positive aspirin effect that, okay, if it have some side effect like platelets aggregation, platelets or bleeding, then, but it can be also used for the heart headache. And nowadays, for the heart headache patient, doctors prescribe aspirin. So there are two outcomes for this mode of action discovery, that any drug should have a positive as well as negative effect, and positive could be the negative effect could be the positive. So, so another very recent example I can just put here. Everyone might become to know about the hydroxychloroquine, and this hydroxychloroquine is nowadays very demanding in a market, because recent paper have shown that, recent research have shown that hydroxychloroquine have some activity against the COVID, this coronavirus associated disease. But this drug actually used for, previously used for the malaria, treatment of malaria as well as some arthritis. But they also, this drug have some activity against the COVID infection, because why? Because people, researchers know their mode of action, because hydroxychloroquine has Klein chemical and they increase the pH, and that's the reason they inhibit the internalization of the coronavirus, because coronavirus bind with the receptor and they go inside the cells, and that require the process called endocytosis, and that endocytosis require the low pH. So if we increase the pH of the cells or endosome, then that will actually inhibit the coronavirus internalization in the cells, and that will inhibit the replication of the coronavirus. So this actually, the function is known before this COVID pandemic, but people use this because they already know the function that, okay, this virus actually go inside the cell through endocytosis, and endocytosis require low pH. If we increase the pH, then might be it will inhibit the coronavirus infection. And there are some, and that's why some country using this hydroxychloroquine, including India and massively USA. But but this drug have also some side effect. That's why they also cause heart attack and some loss of vision. That's why another country recently, they are not using this hydroxychloroquine, even they have an effect against coronavirus. And that country is like most of the European country, they are not using hydroxychloroquine because the toxicity matters. So well, but if we know the function of any drug, then it will be easy to use or repurpose for the different disease as well. So this is quite important to know the function of the drug and mode of action of the drug. So our lab is quite interested and revealing the mode of action of a drug using the growth fitness based assay. And the idea behind the identification of mode of action of a drug is very simple but quite powerful. That suppose if a drug is interacting with two different individuals, and suppose one gene which provide resistance to particular drug, for example, this particular gene is there, they provide toxicity or resistance to this drug, and if this drug is absent, then it could be sensitive because this is missing. So this is quite easy process, but we know that it's very difficult to test this idea in human being, because human have around 18,000 genes, and it's very difficult to make deletion or knock out individuals in 18,000 gene and incubate with drug. So other experimental issue that, okay, just you have a cell line, mammalian cell line, and delete all the 18,000 gene, and that is quite very difficult, challenging task. So there's a recent report about CRISPR-Cas9, but it's very challenging. We are also working on CRISPR-Cas9, but we personally come to know that it's very challenging and very difficult to delete all 18,000 gene simultaneously and just use only single drug to test. But we have another alternate approach using the same growth fitness based identification. So in another model system, which is very close to the human being, that is eukaryotic cells, and that is called yeast, Saccharomyces cerevisiae. Might be everyone know that this is our grandmother favorite yeast species. They actually use for the yogurt and other curd. This is quite famous for using the brewing and baking and as well as biofuel formation. But so this have a very good participant in a technology development. So we are also using this yeast in a drug discovery mode of action. The reason I just told you that this is eukaryotic cells and have only 6,000 genes, and most of the major cellular pathway is quite conserved to the human being, like for glycolysis, mitochondria, TCA cycle, and endocytosis. So almost 90% major cellular pathway, which is very conserved to the human being. And it, even if you have only 6,000 genes, because human have 18,000 genes, but most of the genes are redundant, like 2 or 3 genes actually work for one function, but here only one gene can work for one function. That's why even low number of genes but can participate in the most of the cellular pathway. And another very positive prospect of using this is because it's easy to grow. Within one day you can grow and can do some experiment. And more important is genetic manipulation. You can easily delete all the gene individually and or make the knockout a strain. So, and this is the picture I actually took. This is the yeast. It's also called budding yeast because they form the daughter cell. You can see this the bud, and this is this picture is taken by fluorescence microscopy, and the dye used called chalcophrol white, which bind with the cell wall. So this is the yeast picture. So what I was talking that it's very easy to make all the deletion gene strain for the yeast. So this is a wild type strain. Means one strain having 6,000 gene, 1,000 gene are essential, and non-essential gene are 5,000. So if you want to make a single deletion strain, then what we have used the strategy called barcoded. So easily delete the one gene by homologous recombination. So just we have deleted one gene in a yeast using a specific barcode. Like here, we use the DNA barcode sequence, and this is quite specific. So another gene can be like gene 2 can be deleted by using a different barcode, which is quite distinct from this, that their sequence is quite different. So we have a 2 gene strain, 2 yeast strain having 2 different deletion gene 1 and gene 2. Likewise, we can use another barcode, another DNA barcode sequence to delete another gene and just make it increase the library of the yeast strain. And just likewise, you delete all the 6,000 gene, and we have a different barcode for as a tagging for identification, and we have a collection of 6,000 strain for yeast and deleted by individual gene. So like each strain, like around 6,000 strain here. So now strategy that okay, just use the drug and just grow the yeast strain and test the sensitivity. But these are the 6,000 strain. It's very difficult to grow all the 6,000 strain and treat the all strain with the drug. So this is quite time consuming, challenging, and the lots of expense can be go for this this experiment. So another clever area what we are using, that is what we have done. We just collect all the 6,000 strain in one tube, just and pull together, like all the 6,000 strain is pulled together in a Appin drop tube, a microcentrifuge tube. So all 6,000 strain are here. So all 6,000 strain are here. Now it's not very easy. So now you just use one drug and just test which is sensitive and which is resistant. So no need to test the individual genus strain. So we have this profiling, genome by profiling, that we have all 6,000 strain and just use a drug treated with the drug, like here is a drug treatment, here is without drug treatment, like DMSO control, or just so those strain which will be sensitive. So this strain actually grow for like some time of like 10 hours. We generally use 24 hours and grow in the presence of drug and without drug. So if any one strain which is sensitive to this drug, then their population will be low. So here we can see this this strain is growing slow. So here this population will be less as compared to without treatment. And this population, how we will come to know that this strain actually is sensitive. So because this strain is deleted by the barcode, so what we do, we just extract the genomic DNA and we do the amplify the PCR. So and that PCR can be sent for DNA sequence can be sent for generally we send for the sequencing, and by sequencing we just quantify the barcode, DNA barcode, And here we will just get the read that, okay, this barcode sequence in a treated one is less as compared to without treatment. So, and we just quantify the growth fitness. And so here, this barcode is quite similar in both without treatment or without treatment or with treatment. So this strain is not sensitive, but this red strain, which is quite sensitive in treatment of this drug. So after NGS sequencing, once we will come to know all the 6,000 strain pattern, which strain is sensitive, which strain are not sensitive. And then after, we do some bioinformatic analysis. So we have done this. This is the principle of chemogenomic profiling. So to know that whether this platform is working or not, whether we can, we have developed the chemogenomic profiling technologies is workable for drug or not. So first, what we have done, we use a known drug, which is we already know their function and mode of action, called the ENA, which is actually we get from Dr. Professor Uttam Surana, and they are working on this. This is an anti-cancer agent. This they bind to the DNA. It's a DNA cladding agent, and I inhibit the DNA replication. And this is actually shown that anti-cancer activity. So they already know that this have a mode of action. They bind to DNA cladding agent, but they don't know about what another gene actually participating in providing the resistance. The actual mode of action is not known, but we would expect something, the gene which is correlated with DNA should come in our screen, because the mode of action is already known for this. So first, what we have done, we just test the sensitivity assay of this ENA with the wild type strain, which have all 6,000 strain, and we know the inhibitory concentration. So like 50 micromolar, the ENA actually inhibit around most 80% growth. So for the chemogenomic profiling, because we wanted to know that which strain is sensitive, so we use very low concentration, like only 10% inhibition for the wild type. So so we use very low concentration. So even at this low concentration, if some relation strain is sensitive, that will be quite remarkable. So we use this drug and did the chemogenomic profiling, as we know that they are actually DNA cladding agent. So after treatment of ENA, we followed the same protocol and did the NGS, and we got the NGS result. And this is the gene, this all dot indicating the gene strain related for this gene, and this red dot indicating that this is quite significant, means the more negative p-value means more significant of occurrence. And the y-axis is actually indicating the growth fitness defect, means this RAD 51 is more sensitive, and so more log fitness and more significant values we actually took. So we got around 500 deletion strain is sensitive, but only 200 gene or deletion strain were quite significant in our analysis. So okay, so we come to know, okay, this gene actually quite sensitive with the drug, but what is the function of this gene in a cell? So we utilize the bioinformatic analysis. But before that, what we did, since we had already individual deletion strain in our collection, later we pulled together for here, but we had already individual strain. So to come to know the artifact of the NGS sequencing or this genome-wide experiment, we just go back to our glycerol stock and took the individual deletion strain and check individually. Means at least we can test some of the mutant individually. That is not very time checking. So here we did the sensitivity assay in a microtiter plate assay based. So this is the wild type strain BY4743, and these are different concentration of drug we have used. So these are the color coding is a percentage of growth. So more blue is 100%, and this white is a 0% growth. So we can see this B/4743, the inhibition concentration is 50 micromolar, and whatever we got the here deletion strain deleted for this gene is sensitive, like a RAD one is sensitive around 12.5 micromolar, and this. So most of the gene are quite sensitive, and validating that whatever we got the result in a genome-wide experiment is also true for individual drug sensitivity assays. So our result experiment is working, our profile, our platform is working. But another interesting question that what is the function of this gene? So what we have done, we utilize the bioinformatic analysis. There are lots of online tool in online is available, like a David online or where that can be used to analyze the function of this gene, and they will also cluster the family, cluster the all the gene. Suppose around 200 genes, suppose 10 genes belongs to one function, then they will cluster the one function. Another 10 gene or 15 genes belongs to different cluster, and they will cluster the different family of the gene, which is associated for the cellular functions. So we did that bioinformatic analysis, and we mapped all the gene function, what we got, and we can see that this all the gene ontology which belongs to the ENA, and most of the top hit gene which actually is sensitive belongs to DNA catabolism, DNA repair, and so nucleotide post-replication repair. And this outcome is quite acceptable and because we already know that EN is DNA sensitive, they are actually DNA bind and they cause a sensitivity. And so these all the gene what we found is actually providing the resistance to that drug. So so this result actually validating our chemogenomic profiling, that our chemogenomic profiling is working for this drug. So okay, so this is actually known drug, known function. So what we were interested to find out the antifungal drug activity and their mode of action. So there are lots of groups in Singapore, in our institute and in different institutes within ASTAR is working on antifungal drug discovery, and they have lots of molecules which have shown antifungal activity. And why they are quite interested in antifungal discovery, because this is the actually species which cause the disease called candidiasis, but the disease is not very very lethal when they cause a infection superficially. It can be easily treatable, but systemic infection, once this pathogen is actually move to blood through bloodstream to the different organ, and this actually happens especially in immunocompromised patient, like immunocompromised, the immune system is quite weak. Then this candida species overgrow and transmitted to different body parts and cause the disease. And this is the disease actually is associated with around 60 to 75% mortality rate associated in cancer and as well as HIV. So this is initially actually most of the research actually working on this Candida drug discovery. The reason because they have only limited drug. So I just show you this is a superficial infection which can be easily treatable, but this all the brain cerebral candidiasis and this chronic mucocutaneosis is all the systemic infection which is quite lethal. So why they are working? Because there are lots of drug actually developed during this 50, 60, 70 year, but only one drug is potent to kill the cell. Other remaining only one drug like amphotericin is used for the systematic candidiasis. Other drug is fungistatic. They cannot kill the cell. They only stop the candida. But only amphotericin is a drug which can kill the candida. But since this drug is quite associated with toxicity, cause liver cirrhosis and kidney damage, so that's why this drug is the last option. So that's why the lots of group all over the world is working on to find the good antifungal drug. So as I mentioned that there are lots of groups. So we got a different antifungal compound like hypochlorite from Dr. Suvi and Dr. Yoganathan. They are working on hypochlorite, and another drug, aureomycin, we got from Dr. Fong Tian, peptide 50. We got from Dr. here, Brian Chia. So, and this is also autolinium bromide. So we know molecules are actually antifungal activity, but we were quite interested to know the mode of action, which is quite important in drug development, as I mentioned before. So just I'm going to show only one example of the hypochlorite. So hypochlorite is actually bioactive natural product extracted from Acromonium species, and that group extract and purify, and our group actually deliver the mode of action study. So this hypochlorite actually is a sphingolite based like compound, have sugar molecules, long fatty acid, and an amino alcohol group. And here this Candida albicans in vitro concentration is around say 1.6 micromolar, and the model organism what we are using for mode of action determination, cyclosensitivity, they're almost the same concentration is in with IC50. So we did the chemogenomic profiling, and we got this top heat of biological function, which provide resistance to this hypochlorite belongs to the endocytosis, vacuolar transport, intracellular transport. They belongs to the similar same cluster of the vesicular trafficking in a cell. And what is the vesicular trafficking in cell? This is quite important. And as I mentioned that the drug hydroxychloroquine also follow and inhibit the endocytosis previously. We also got that hypochlorite inhibiting the, from the chemogenomic profiling, that they're inhibiting the endocytotic process. And what is the endocytosis? This is the quite important cellular function, and most important because most of the cells protein transferred from plasma membrane and just recycled to go to the vacuole, and also and so go to the Golgi bodies, which is the site for the production of synthesis of protein, like endoplasmic reticulum, Golgi body, here the main center where protein synthesized and post-translation modification, and this protein goes to the back to plasma membrane. So these all the cycle is called the endocytosis and vesicular trafficking process, and one of the process called endocytosis. And since we got that this hypochlorite drug actually is causing the defect in the endocytosis process, because most of the gene we identifies belongs to this pathway. So our model is that might be hypochlorite bind to the plasma membrane, and they bind to this internalized membrane of the initial endocytosis site, and they just go to the different pathway following the pattern as what actually this follows. So in mammalian cells, and ultimately they goes to the vacuole, and this vacuole is equivalent in a mammalian cells called lysosome, and they disrupt the vacuole. So to confirm that hypochlorite is disrupting the vacuole, because most of the gene we identify belongs to the vacuolar synthesis and endosome transport. So here what the gene we identify in chemogenomic profiling, we did the same individual sensitivity assay, and as we can see, as compared to the wild type cells, these all VPS vacuolar protein or vesicular trafficking protein deletion strain is sensitive as compared to the wild type cells. So validating our result that hypochlorite inhibiting the vacuolar function. So further we validated using another experimental method and confirmed that hypochlorite actually affect the vacuolar morphology. What we have done, we use a drug called FM464, which bind to the plasma membrane and internalize to the vacuole. So here we can see this is the is treated with without hypochlorite DMSO control and strained with FM464 dye, and this small circle is like 1 or 2 here is a vacuole of the yeast cells, but in this vacuole is quite fragmented in treated when the yeast cells are treated with the hypochlorite, confirming that hypochlorite mode of action is inhibiting the function of endocytosis and disrupt the vacuolar structure. So here one of the experiment example I have shown for antifungal activity and their mode of action. Likewise, we have also chemogenomic profiling for other antifungal drugs. So, but another quite important subject and research matter I'm gonna show about the environmental factors like the pollution. So we know that this plastic is quite is very dangerous for the human being and all the ecological system. So we wanted to know that is there any interaction of the plastic, any cell interaction, any genetic interaction, because we all know that plastic is lethal and quite dangerous for human beings and all living organism, but we don't know what is the mode of action. And this is quite important uh, subject or a research area in Singapore to come to know about the molecular mechanism of mode of action of different environmental factors, toxic chemicals under ToxMed program. So we got grants to know the mode of action of the plastic, so that people come to know that if there are some mode of action, then we can easily prevent their associated disease. So what is the plastic? So we know that most of the plastic is synthesized by the phthalate is phthalate, which is actually the toxic chemical. And this phthalate is used for the plasticizer to make plastic more compact, more stable, and for durable. And this is the phthalate is actually ester of an aromatic dicarboxylic acid. And this plastic come to the human or cell interaction through different route, like through the water, air, and through the soil, and ultimately it reaches to the human being, and it affects the liver and reproductive system, kidney, and brain. But what is the mode of action is still don't know how this phthalate actually is toxic. So there are lots of phthalate molecule, but one of the molecule which is used for plasticizer called DEHP. But DEHP is not itself is toxic. So we can see here that DEHP, when we grow the yeast cells with DEHP, there's no any lethality, and this is quite consistent result whatever the published for the mammalian cell, that DEHP phthalate, which is actually used for plastic formation, is not toxic. But why phthalate is toxic? Because once DEHP is entered inside the cells by pancreatic enzyme lipase, they just leave the DEHP and form a active metabolite phthalate called MEHP. So that MEHP is actually is responsible for toxicity of a human being and cause a different disease. And so here we can see the DEHP also inhibit in a yeast cells and around 9 millimolar. So, but what is the mode of action of MEHP? So we did the chemogenomic profiling and identify the gene responsible for resistance, providing resistance to the MEHP, and we got all the genes associated for providing resistance to the this MEHP. So what is the function of this gene? We just got from bioinformatic analysis, and quite interesting that this MEHP is binding to the plasma membrane, because plasma membrane genes actually coming as a top hit for providing resistance to MEHP, and the same component esterol and steroid biosynthesis, which is the quite important part of the plasma membrane integrity also coming. And likewise another tryptophan biosynthesis process and vehicular transport, which initiates the deletion strain, which is the gene which is associated for the ergosterol biosynthesis, is quite sensitive. So further we confirm that MEHP bind to the plasma membrane and cause the toxicity. So we did another experiment where we utilize one dye which is positively charged, like propylene aldehyde, and they bind to the plasma membrane, because plasma membrane have a negative charge, so it's very difficult to use the negative charge dye. So we use indicating that all the cells are quite viable, but the untreated cells, we can see that there's a PI is more enrichment and more at 9 millimolar, which is a complete 100% inhibitory concentration for yeast. Here all 100% cells have a PI internalized, indicating that MEHP disrupt the plasma membrane and allows to enter the PI, and that is the actually cause for the sensitivities. And as we have as I show you, that DEHP is not able to inhibit the yeast in yeast as well as in mammalian cells. So here we also see that even higher concentration DEHP, hardly we can see any PI internalization, indicating that DEHP is not causing any plasma membrane defect. That's why they are not program, which is quite interesting research program of Singapore government. They wanted to test the mode of action of all the toxic chemical. They have a bunch of toxic chemical, and which is toxic for the cells. And it's good to yeast is a quite good model system, because we cannot see that, we cannot check and the equivalent mammalian cells is very difficult to test all the toxic chemical in a row. But in E cells, we can use this high throughput screening, and we can simultaneously check the sensitivity pattern of all 6,000 genes in a one parallel experiment. So this is a good platform to for different groups. And another group like food and nutrition technology. Recently, Singapore have established this institute. They also wanted to know the mode of action of some flavor, fragrance, and we have some result. They are using some fragrance. They wanted to overproduce some fragrance and as well as some biofuel like methanol. So we can with disease like metabolic disease, cancer, diabetes, and so and in parallel we are uh, also revealing the mode of action of different metabolic disease inhibitor, and in parallel with the fungal and bacterial inhibitors. So finally, just I would like to acknowledge all the people which have a very collaborative interaction with our group, our postdoc supervisor, Dr. Prakash Nurgam, and this hypochloride I just mentioned that this one group is working on in a natural product library. They are quite interested, and this the Dr. Lishin is with us, and a very big thanks to our collaborator Dr. Sean Hun, who actually is doing the NGS analysis and as well as some requirement for RNA-seq analysis. And we also have a collaboration with the father of P53, called Professor David Land. We have also published some paper, international paper with as a co-author with David Lane, and they are actually looking in the inhibitor for P53, which is quite important protein in a cancer. So they wanted to know they're investigating the staple peptide inhibitors which actually inhibit the interaction of P53 and M2. So thank you so much for your patience, and I would like to go for any question if you have.
Thank you, Dr. Mohammed. That was an excellent talk on the importance of chemical genetics platform in diverse areas of, you talked about how it has been discussed in the ways of hydroxychloroquine and corona disease, as well as the very vastly important problem of plastics and their rampant usage and the effect on the human metabolism. Thank you so much for such an excellent talk. And there are quite a number of questions which are there. Shall we move to the questions now?
Yeah, sure.
Dr. Mohammed?
Yeah.
Okay, so we will gradually proceed to the questions part. Is there any role of E-selectin in vesicle trafficking?
Because, yeah, of course, selectin protein, right?
Right.
Yeah, so there's a quite homologue in E cells for the selectin. So this vesicular trafficking in human as well as E cells is 100% conserved. So whatever the protein in human is also in yeast. So there's no any but the name is quite different. But they have a selectin in a human being. Sorry, in E cells. Yeah.
Okay, and as I can see, there's another one question that regarding sodium azide. So have you used sodium azide for your experimentation? Did you use it somewhere? So
yeah, sodium azide, as we know, this is a mitochondria TCA inhibitor, right? This is azide with oxygen. This is oxygen terminal steps of energy generating step in TCA cycle, electron transport chain, right? So we use this sodium azide is actually, so we have not used sodium azide, but there's a literature, but there's no any report. But that actually is in our under list, sodium azide and antimycin, and these all are electron transporter inhibitor. So we are just working on different inhibitors, but we have not done chemogenomic profiling for sodium azide. Yeah.
Okay, so one thing is that with regards to the plastic metabolism which you talked about, that how DEHP is not actually the toxic, but when it is metabolized by lipase, it turns toxic. So what is the time frame which you are looking at to it, and what kind of ways can we avoid this kind of a toxicity in our body? Is there any
So,
specific plastic which can be used? Yes.
yeah, so Miss, yeah, we have to be, get rid of this this phthalate. That's why nowadays whatever the plastic is used called phthalate free, because phthalate is a quite good is a very much dangerous for the human being, and especially for the children. And because they directly bind to the plasma membrane and straw, we have investigated that they bind to the straw. And recent one report have also shown, that is not genome bind, but they also shown that this phthalate MEHP is bind to the estrol in mammalian cells, and this estrol is more rich in testosterone hormone, so it's quite associated with infertility. And infertility, about 40% case of the USA there's a WHO report that they're actually struggling for the infertility. So that's the quite basic problem. That's why the Singapore government and all over the world is looking for why we should not use this plastic. So the first cause is infertility, and we have a report that that could be possible because they can bind to the estrol, and that is a more rich. But why? Just you mentioned that DEHP, so we have to completely get rid of the phthalate. Or
right.
Yeah, so that's the main aspects.
Okay, so Dr. Mohammed, we have a question here from the Dean of the School of Pharmaceutical Sciences. Professor Anupama, are you there, ma'am?
Yeah, I wanted to know actually, कल से मेरा zinc उस दिमाग में घुस रहा है, that how zinc act over here as antifungal. That is what I wanted to know. If he has some idea.
How zinc actually inhibit the antifungal activity. So I don't have any
in
idea.
this particular COVID situation, because yesterday in one of the scenario, one of the presentation, he has mentioned that zinc can be used. So if that is the scene, then how zinc will act as an antifungal?
No, I have not mentioned that zinc is already well established that is antifungal activity. That's why there are lots of there's a lots of medicine which is cream, right, against fungal activity. They have a zinc. Okay, so zinc already have antifungal. But you have a two question, I think. So if I'm not wrong, then why some of the recent research have shown that zinc could be is good for the anti-COVID, right? The first question. So zinc actually inhibit the viral replication. Yeah.
Okay.
So one of the function of hydroxychloroquine, other than increase the alkaline pH, they also actually help to transport the zinc from the outside the cells. So more and more enrichment of zinc. And there are lots of paper in PLOS Pathogen and very reputed journal. They have shown that not for only COVID, zinc is the inhibitory for the DNA RNA replication. So that can be the so that is the connection. But that is just one question. And what is the zinc? What is the mode of action of zinc as an antifungal? So they are also inhibiting the this RNA function. Yeah, and as well as they also induce the hyperosmotic stress. So another mode of action for the zinc. Yeah.
If I'm not taking too long, this plasma substitute, I do not digest that. How come there are some papers which we have been seeing that plasma substitute is it that safe therapy to be used in this COVID situations, patients?
I don't know. See, I don't have any knowledge about the COVID. Right? I'm not going to talk about the COVID. Sorry, but just I just took one. I don't have any experience, but just I took one example for the drug repurpose, right? Because my just talk that I just bring this hydroxychloroquine because why people are using hydroxychloroquine because it have a function to increase the alkaline pH, and that is the mode of action against malaria. Malaria and as well as arthritis, they increase the pH. In malaria, parasite falciparum, Plasmodium falciparum, they don't have a lysosome, they actually have a vacuole, so they increase the alkaline pH and they inhibit the formation of heme, which is they digest from the hemoglobin. So they increase the mode of action of hydroxychloroquine is all increase the pH. And we know that COVID, what is COVID or any other virus, like they bind to the plasma membrane. They have to bind to the plasma membrane to internalize inside the cells. Okay, and once they bind to the plasma membrane, they will go inside the cells. Because they have to replicate. They need more and more nutrients and more substitute, more like carbon and nucleotides to replications. They have to go inside the cells. So first they bind with the plasma membrane, and through the endocytotic process, they inside the cell, and they just come out from, once the lysosome degraded inside the cell, their RNA come out from in the cell, and they further replicate and form more and more virus. And through exocytosis, another more virus will go to the another cells. So this is actually a process of the life cycle. So hydroxychloroquine is the only one function. They increase the pH. If pH is increased, then endocytosis mechanism will not occur. And that is the mechanism. That's why there's several papers in very Nature and Nature Medicine, and they have shown the activity of hydroxychloroquine inhibitory effect. And that's the only mechanism they are predicted. Yeah.
Madam, does that answer your question?
Hello. So is
hello. Okay. So Dr. Alfata, we have a question here from Dr. Jishan. So Dr. Jishan, please go ahead with your question.
Yeah, 1 minute. Dr. Alfata, I just want to ask that you were doing a lot of chemogenetic profiling. So I just want to explore one thing that about the CYP gene family, which has a very lot of good role in drug metabolism and all. So have you looked on any CYP gene family to chemogenetic profiling, the role of it?
Sorry, Annie?
I said that there is a family, CYP gene family, which the genes are responsible for drug metabolism. So I just wanted to know, have you looked on any of the CYP genes through chemogenetic profiling, the role of it?
So we have not actually visited that type of drug, but each drug have a different profile, right? So we just we want to know more mode of action of different drugs. So we have not come to so there's one drug metformin we have used, that is anti-diabetic drug, right? So still metformin, the mode of action is still not known, but still that is okay, and people are using for anti-diabetic. So we come to know, but not exactly, but we come to know that what gene actually participating in a metformin activity. Exactly how metformin is working, we don't know. So, and metformin inhibit the glycolysis metabolism. So yeah, that's we have some answer there.
Okay. So in the near future, you must be planning to have some chemogenetic profiling for cytochrome.
Yeah. Thank you.
Okay, Dr. Alfata, we have a question here from Dr. Rani Mansoori from School of Pharmaceutical Sciences. She's asking that how chemogenomics approach can be used for screening of drugs and comparison in SARS and COVID can be implemented, and how can be implemented?
Yeah, for SARS, we know that there's two different approaches, because whatever the protein, whatever the cellular protein component of SARS is required to attach the cell and cause the disease. So one component, other component, and whatever our cell is helping to bind the SARS virus and internalize inside our cells, right? So we know that SARS, we can look at some endocytosis. We can screen lots of drug and identify the drug which inhibiting the endocytosis. So since I just mentioned that hydroxychloroquine is a drug that have a lot of side effects. So we can see another drug, there are lots of NPL, like India. India have a diverse and have a plenty of natural product using Ayush program from the government of India. They have a Ayurvedic, Unani, and there are lots of Himalayan products. But we don't know the mode of action, so that's why we cannot go directly. But in the first I just mentioned that aspirin. Okay, that is good for some disease, but that is also bad for some disease. Bad. So both have a positive as well as negative effect. So until and unless we don't know the mode of action, we cannot blindly give the drug to the patient. So we have to be very careful. We cannot see. I just take one good example. We know that we have a molecule which inhibits the viral. We say that okay, we use soap. We clean our hand by using soap so that we cannot get the virus infection. So we have a molecules, right? We have a detergent which actually disrupt the cell membrane and all, and that kill the virus. So we have things, and that we can get in a 2 rupees, 3 rupees soap, and we are killing the virus, but we cannot eat, right? Like was a very good example in Iran. Some people have said, oh, they are using 70% alcohol to sanitize and kill the cells, COVID virus, and they all drinking the ethanol. And some people instead of ethanol, they drink the methanol, and that is toxic.
That's very toxic, right?
Yeah, that's very toxic. So, and here you cannot eat the soap and cannot drink the methanol and all. But we have molecules, but we have to know the mode of action. So that's the quite important. We cannot go directly.
Right.
Yeah. So that's why we can screen lots of drug which does not have a toxic effect, and if that is actually inhibitory of the endocytosis or any other process which helping the cells, which helping the virus to bind the cells and it causing a SARS and another COVID virus infection, right? Then we can easily use that drug. So here we can.
Right. So Dr. Al-Fatah, we have another question from one of our students over here. She's asking that apart from target-based drug discovery, are there other applications of chemogenomic screening?
Yeah, I just mentioned in a summary that see, chemogenomic profiling, like the basic principle, we have to identify the mode of action. That is the platform. Okay, so like for one of the best example, recently we have identified the gene which increase the production of fragrance, lactone. So lactone is used in a fragrance and a lot of food application. Right. And this is highly demanded. So using chemogenomic profiling, what we do, we first find that which gene actually sensitive with particular lactone, because it cannot overproduce inside each cells more and more lactone, because that is quite toxic for the cells, right? So we have to identify the gene which providing to the toxicity. So once you identify that gene, then you overexpress. And so your cells become quite tolerant to that lactone or whatever you want the metabolites. You can increase. So here the one of the application, and we are working on it. Yeah.
In fact, I have worked with one of the enzymes, pyroxenase 1, which is responsible for degradation of the lactones in the body. Okay, that's a very interesting, right?
Yeah, I'll just say, yeah, thanks.
Yeah, Dr. Al-Fatah, we have another question from our faculty members here that she's asking, Ms. Padmaja Rao, she's asking that multiple genes in combination are involved in metabolism of a drug. Does your chemogenomic approach or model help in understanding that?
Yeah. Because here we are not looking for all the gene. We are not going the like reverse genetics, right? Reverse genetics means we have some we have phenotype, like particular gene actually is cause the cancer. And now identify thousands of molecules or drug which inhibit that gene, right? And so, but we actually using a forward chemical genetics. We have a bunch of drug and just find the mode of action and then utilize based on the requirement.
I would like to now invite our Dean, School of Biosciences, Professor Vyasam Singatkari to kindly say a few words about the webinar.
Thanks, Dr. Khan. I think I should extend my sincere thanks, and we are really obliged to Dr. Al-Fatah for accepting our invitation in a short notice.
Yeah,
I think it was a very good lecture, quite informative. So I have two questions I would just ask before I complete everything.
Please, sir.
So with this chemogenomics direction, have you able to launch any drug, or have you identified any drug that is currently in the various stages of the development?
No, sir, yet we have not launched any drug, but one staple peptide that is actually inhibitor of p53 and MDM2. We almost close to first file for the patent, because that is an inhibitor for anti-cancer activity. And
any idea about sorry, you're continuing?
Yeah, so might be that would be the drug first we will go, but yet we have not launched any drug. Yeah,
Okay. But there are series of molecules in the pipeline?
We have 2-3 drug against antifungal activity, and one is for the cancer. Yeah, one for the cancer. Yeah.
One more question is whether synthetically any antibody against COVID can be developed using this mode of operation, chemogenomics.
If that
I have been given to understand,
yeah,
a Harvard-based company, Virna Therapeutics, is working towards it and has produced, a synthetic antibiotic, and currently they have shown a very good antibody and antigen reaction with the ACE2 inhibitor. Whether it acts against S1 and S2 or not is not known, but yes, definitely. A similar approach has been done in your lab, because A-Star is a very well-known company. I think it's a rather very good venture capitalist.
Yeah, yes, I agree.
Yeah.
But we cannot what we can do, we can just come to know their side effect. If some group have some antibody against the virus or for any things, right? Then what we can do, we can identify their off target using this technology. Yeah.
Okay. So I was asking about synthetic. So synthetic antibody could be having less side effect as compared to the recombinant one. That was my idea. So what's your idea about it?
It depends upon the binding, off-target binding, right? Some of the synthetic is quite good, and they have even very low concentration. Until now, but I realized that we have lots of synthetic molecules, but they require higher concentration, but they have a good activity. But some, as you mentioned, that some antibody, conjugate antibody, if that actually require higher concentration, have some another off-target binding, then that would be not beneficial. But if some synthetic, which have a very high efficient binding and quite a specific target, then that would be good. So it depends upon the binding, how they actually specific and require more requirement, the concentration. Yeah, so unless we screen and do the experiment, we cannot say things. Like for example, the rapamycin as drug is a well-known inhibitor of the nutrient signaling, rapamycin. And that drug, very low concentration and very specific. They don't have any side effect. Yeah. And
thank you so much. Yeah. Thanks a lot. Thank you so much. And I think from my side, as well as from University, Apeejay, Stya University, and School of Biosciences, and in general from Apeejay family, extend warm thanks to you for accepting a short notice and making such a nice lecture in a given moment of time, and has helped our students as well as all the faculty members to understand the very complicated subject in a very lucid and illustrated language. Thank you so much.
Thank you so much for this wonderful opportunity, sir, for interaction of your own faculty member and student. And if you have any student and faculty member have any question, then I would be very happy to get by on email, and I would like to also further interact. And since the interaction is quite important in science, more collaboration, more interaction is good for research.
That would be great. That would be really great opportunity for us. Yeah. So we'll definitely extend all this invitation to all of our students, sharing your email ID to them, so that if anyone has any questions, they would directly write to you.
Yeah. Thank you so much, sir. Thank you so much.
Thanks a lot. Thank you so much.
Thank you.
Thanks, Dr. Kar.
Yeah. So to end with, I would like to thank you, sir. And I'd like to thank Dr. Mohammed Al-Fatah for such an in-depth focus on chemical genomics and approaches. And this webinar is a part of an ongoing series of free webinars, which is being organized by the School of Biosciences at Apeejay University, where we are bringing eminent scientists and industrialists to talk to us and our students and our faculty members likewise on various research topics of contemporary interest. So we'll keep that up. So I urge all of you, our wonderful audience, to please visit our university website, where we'll be sharing more information on that. And at the end, I want to say a big thank you to our audience who very enthusiastically participate in our talk. I wish you all a very safe stay in your homes. Thank you so much. Thank you, Dr. Alfata. Thank you, everybody.
Thank you, Dr.
That's
Subra.
Thank you. Thank you so much.
That's all
Thank
for the webinar. Thank you, everybody. Thank you so much.
Thank
Yes.
you. Thank you,
Cheers.
Dr.